Okay, so welcome everyone to one more edition of our Student Algebraic Geometry and Foliation Seminar at INPA. Today it's my pleasure to introduce my mathematical colleague, Brady Ali, who I could meet at INPA some years ago in a summer course. And it's nice to see her again as a mathematical colleague in algebraic geometry. And Brady took her master degree at Unicamp, and now she is doing her PhD studies at University of Waterloo under the supervision of the professor Uxandra Moraru. And now she will talk about a different way to generalize the Weierstrass semigroup. So, Braid, feel free in our seminar. Go
Thank
ahead.
you. Okay. Thank you, Eduardo. Thank you for the introduction and thank you for having me today. So, as Eduardo said, I'm going to talk about a different way to generalize the Weierstrass semigroup. So, this is a research project I did at the University of Campinas under the supervision of Professor Marcos Jardín. So, basically, we studied the Weierstrass semigroup and then we proposed a different way to generalize this Weierstrass semigroup. So, first, I'm going to give some basic notions and then I'm going to define the Weierstrass semigroup, and then I'm going to define the generalization that we gave of the Weierstrass semigroup, and I'm also going to explain some properties that we found of this generalization. So in this talk, I'm going to denote by Z plus the natural numbers union zero, and we are going to work always on an algebraic closed field K. And X will always be a non-singular projective curve of genus G. And Kx will denote the function field of X. That means its elements will be the rational functions on X. And I'm going to define a divisor on a curve. So a divisor on a curve is just a finite sum of coefficients ai and points pi, where these coefficients ai are integers. So the degree of this of a divisor in a curve is just defined as the finite sum of these coefficients ai. And we say that divisor D is effective if every of these coefficients ai are greater than 0. And also we have that a divisor of a of a rational function f can be written as the divisor of its zeros minus the divisor of its poles. So the divisor of a function can be written as a finite sum of ni pi minus the finite sum of nj qj, where these are the zeros that has this rational function of order ni at the points pi, and here are the poles that has these rational functions at the points qj of order mj. So we said that a divisor is principal if D can be written as the divisor of some rational function. So now I'm going to define this sheaf. So if we have an open cover of X, then we define the sheaf OXT as the rational functions such that D plus the divisor of this rational function is greater or equal than 0. And I'm going to denote by H0 of OXT the dimension of the global sections of this sheaf. So how can we interpret these rational functions that belong to this sheaf? So if we write this divisor D as the finite sum of ni pi minus the finite sum of nj qj, where ni and mj are greater than 0, then these rational functions that belong to this sheaf are going to be such that f has zeros of order greater or equal than mj at the points qj, and f may have poles only at the points p1, pr, with pole order at pi being bounded by ni. So these rational functions that belongs to this shift satisfy these two conditions. So now I'm going to introduce the Riemann-Roch theorem. And the Riemann-Roch theorem helps us to find the dimension of this shift. So the dimension of this shift is equal to the degree of the divisor d minus g plus 1 plus the dimension of the shift OX of kx minus d, where kx is the canonical divisor of the curve x. So I am also going to work with vector bundles. So we have the Hirzebruch-Riemann-Roch theorem, and this theorem helps us to compute the dimension of the global sections of a vector bundle. So if we have a vector bundle over a curve X of rank R, then we have that the dimension of the global sections of this vector bundle minus the dimension of the first cohomology group of the vector bundle is equal to the degree of E plus R times 1 minus G, where G is the genus of the curve X. So in the case when E is a line bundle, we know that E can be written as OXD, where D is some divisor. So if we replace this E here in the Hirzebruch-Riemann-Roch theorem, we are going to get the Riemann-Roch theorem. So I'm also going to need the definition of a vector bundle that is semi-stable. So we say that a vector bundle on a curve X is semi-stable if for every proper non-zero subbundle f of E, we have that the slope of f that is equal to the degree of f over the rank of f is less or equal than the degree of E over the rank of E. So this number here, the degree of E over the rank of E, is called the slope of E and is denoted by mu of E. So there is an interesting proposition that says that if we have a vector bundle that is semi-stable, such that the slope of that vector bundle is greater than 2g minus 2, then we can get rid of the part h1 of xe. So we only have that the dimension of the global section of the vector bundle, the sections of the vector bundle, is equal to the degree of E plus the rank of the vector bundle times 1 minus G. So we don't have to worry about the first cohomology group of the vector bundle. So now I'm going to define what is a numerical semigroup. So a numerical semigroup is a subset of the positive integers such that 0 is an element of this set. And if we have two elements, x and y, then the sum of these two elements also is in this set H. And the complement of this set needs to be finite. So, and we also have an invariant of this numerical semigroup that is called the genus of this numerical semigroup and is defined as the cardinality of the complement of this numerical semigroup. So as an example, we have H defined as 0, 4, 6, 8, 9, 10, 12, 13, and so on. So this is a numerical semigroup because 0 belongs to H. And if we take any two elements of this set, then the sum is also going to be in H. And the complement of this set with respect to the positive integers is 1, 2, 3, 5, 7, and 11. And we can see that the complement is finite. So this set satisfies the three properties of a numerical semigroup. So we can conclude that this set is a numerical semigroup. So now I'm going to define the Weierstrass semigroup. And so we fix a point P on X, and we define the Weierstrass semigroup as all the positive integers such that there is a rational function that has a pole of order n at the point P. So it can be shown that this Weierstrass semigroup is a numerical semigroup. And the study of the Weierstrass semigroup is important because it helps us to understand the geometry of the algebraic curves, and also it has a lot of applications to code theory. So there is an important set that comes from the Weierstrass semigroup that is called the set of gaps, and is the complement of the Weierstrass semigroup. So since we know that the Weierstrass semigroup is a numerical semigroup, we know that the complement is a finite set. So we call this the complement, the set of gaps, and we denote it by GP. And this is defined as all the positive integers such that there is no rational function uh, that has a pole of order n at the point P. So the elements of this set of gaps are called gaps, and there is an important theorem about the set of gaps that is called the Weierstrass Gap Theorem that says that the cardinality of this set of GP will be equal to G, the genus of the curve. And it also says that if we order these gaps, the elements of this set, then the first element will be equal to 1, and the largest gap, this one, will be less or equal than 2g minus 1. So for example, we have the Klein quartic over the complex numbers, and is defined by this equation. And if we take the point P001 in the Klein quartic and we compute the Weierstrass semigroup at this point P, this will be equal to 0, 3, 5, 6, 7, and 8. And so we know that the genus of the Klein quartic over the complex numbers is equal to 3. So if now we compute the complement of this set, we have that the complement, the set of gaps, GP, is equal to 1, 2, and 4. So so the cardinality of this set is 3, and we have that the Weierstrass Gap Theorem is satisfied. So now I'm going to explain what was the definition that we gave of the generalization of the Weierstrass semigroup. But first, I'm going to explain what was the motivation behind the definition that we gave. So if we recall, the Weierstrass semigroup is defined like this. And we can also write this definition in terms of global sections. So the Weierstrass semigroup will be defined as the positive integers such that the dimension of the global sections of the sheaf of x n minus 1p is less than the dimension of the global sections of ox n p. So as you can see here, I'm just taking out 1 point. So here I have np, and here I'm just taking minus 1 point p. So in the book of the Geometry of Algebraic Curves, written by Arbarello, Cornalba, Griffiths, and Harris, they introduce the concept of the Weierstrass semigroup at 2 points. And they define it like this, as the pairs n1 and 2, such that there is a rational function that has a pole of order n1 at the point P and has a pole of order n2 at the point Q. And later, this definition was also generalized to endpoints. So the Weierstrass set of endpoints, P1, Pn, is defined as the positive integers n1 until nm, such that there is a rational function that has a pole of order m1 at the point P1 and has a pole of order mm at the point Pn. So again, we can write this definition in terms of global sections, like this. So we have that this set is equal to the positive integers n1 mm, such that the dimension of the space OX of the sum of mi pi minus pj is less than the dimension of the global sections of the sheaf OX of the sum of the points mi pi for all j's that goes from 1 to n. So as you can see here, I'm taking the pj point. So I'm taking minus this point. Here I have the sum of all the points, and here I'm just taking out the point pj. So now we can also define the ith root of this definition. So here we have. So now we define the ith root of this definition of this set. So this will be equal to the positive integers such that the dimension of this space oxn minus 1 pi plus the sum of all the points pj where j is different from I is less than the dimension of the space ox and pi plus the sum of the points pj where j is different from I. So as you can see here, I'm just taking the ith coordinate of this definition. So I'm taking just the mi. So that's the reason I'm taking here the point pi. So here I have all the points and I'm taking in this part the point pi. So now this chip is equal to the tensor. So this chip is equal to the tensor product of these two chips. And equally, this chip is equal to the tensor product of these two other chips. So if I take f equal to this chip, the sum of all the points pj where j is different from I, and I use this notation where f and p is equal to f tensor with ox and p, then I can rewrite this definition as the positive integers such that the dimension of the sheaf f n minus 1 pi is less than the dimension of the sheaf f n pi. So this is what motivates this generalization. And I'm going to give the definition of the generalization we gave here. So if f is a sheaf of ox modules and p a point in x, then the Weierstrass set of f with respect to p is defined as the positive integers such that the dimension of f n minus 1 p is less of the dimension of the sheaf of the globalization of the sheaf f n p, where f and p is equal to f tensor with ox and p. So if we take f equal to ox, the sheaf of degree 0, we can recover the definition of the Weierstrass semigroup at the point P. So in this case, when f is equal to ox, we have that SFP will be equal to HP. We have the definition, the normal definition. So we can also define the set of gaps of this set. So the set of gaps will be the complement of this set and is equal to the positive integers such that the dimension of the space f and p is equal to the dimension of the space f n minus 1p. So now we wonder if this set is a numerical semigroup. So it turns out that this is not a numerical semigroup. However, it satisfies this property. So when we have H to be a numerical semigroup and E any set, then we say that E is a relative ideal with respect to H if H plus E is a subset of E. So we were able to prove that the SFP, that this generalization is an HP relative ideal. For that, we just have to define this action and prove that this is well defined. And we were also able to prove that if F is a semi-stable bundle, then the largest gap of this set of gaps, will be less than 2g minus the degree of F over the rank of F. So for this definition, we were not able to compute the cardinality of this set. We were only able to see that the largest gap will be less than this number. So, okay, so
Brady,
yeah, yeah,
I have a question. Can you
yes.
recall the definition of the degree of a vector bundle?
Oh, yes, sure. So the degree of a vector bundle is the degree of the, so a vector, we can associate to a vector bundle, a line bundle that is the determinant of the vector bundle. And so since the determinant of a vector bundle is a line bundle, then we define the degree of a vector bundle as the degree of the determinant of the vector bundle. And oh, yeah,
Okay, perfect. I got you. Thanks.
okay, thank you. Okay, so recall that. So these were our definition of the generalization of the Weierstrass semigroup. And so we decided to generalize this even further. So instead of taking a point P, we decided to take a divisor D. And we define SFD as the positive integers such that the dimension of the space Fn minus 1D is less than the dimension of the space Fnd, where Fnd is F tensor with Oxnd. So why we decided to do this? So here is our motivation. So there are semigroups that cannot be realized as the Weierstrass semigroup of a point in a curve. For example, we have in this article, we have one example of a numerical semigroup H of genus 16, such that this semigroup cannot be realized as the Weierstrass semigroup of a point in a curve. So we ask ourselves these questions. So are there semigroups that are not the Weierstrass semigroup of a single point, but arise as the semigroup of several points or one point with respect to another? So this is the reason we decided to generalize this further to a divisor D. And we found nice properties of this definition. So, okay, so it can be shown also that if n belongs to this set, our new generalization, then we have that there exists a rational function such that the divisor of poles of the divisor of f plus e is equal to nd. And so as you can see, here we can see this set as a Weierstrass semigroup. So we call this set, instead of SFD, now we call HAD, and and this will be the definition of HED, and it's called the Weierstrass set of a divisor E with respect to the divisor D. And the set of gaps is defined as the complement of this set. So it's defined as all the positive integers such that there is no rational function with the divisor of poles of the divisor of f plus e equal to n times t. So now I'm going to explain some properties that we found of this definition. So we found that in the case when E is an effective and principal divisor and D is an effective divisor, this set is going to be a numerical semigroup. So it's going to satisfy all of these three properties. Zero will be here. If we take n and m in this set, then the sum is also here. And the complement of this set is a finite set. And we also found that the largest gap, in the case when D is an effective divisor, the largest gap, the largest element of this set will be less than 2g minus the degree of E over the degree of D. And so for this case, when we had a divisor D, we were not able to find the cardinality of this set, but when we have D equal to a point P, so in this case, we were able to find the cardinality of this set. So when D is equal to P, we will have this definition. It's just replacing instead of the P. And also, it turns out that this set, HED, is known in code theory. And this set, this GEP, is called ECAPS. And using this notion in the article Consecutive Weierstrass Gaps and Minimum Distance of GOPA codes, they use this definition to improve the lower bound for the minimum distance of the GOPA codes. So, so, so this GP is our original set, the set of gaps of the Weierstrass semigroup, and we have that if n belongs to GP, then n is less than 2g, and the cardinality of this set is equal to the genus of the curve. So, and in general, uh, for any divisor E, we have that if n belongs to the set of gaps GP, then n is less than 2g minus the degree of E. And so note that if the degree of E is greater or equal than 2g minus 1, then this set will be just a null set. And so we found, as I was saying, we were able to find the cardinality of this set when D was equal to just a point P. So in the case when the degree of E is less than 2g minus 1, then the cardinality of this set is equal to the dimension of the space OX kx minus E, where kx is the canonical divisor of x. So I'm going to, okay, so when E is equal to 0, we have that the definition GEP is equal to the set of gaps GP. So if this theorem is correct, it should also satisfy the Weierstrass Gap Theorem. So if we compute the cardinality of G0P, from this theorem we have that is equal to the dimension of OX kx minus 0. And using the Riemann-Roche theorem, we have that this will be equal to G. And as if we recall, the Weierstrass Gap Theorem tells us that the cardinality of this set is equal to G. So in the case when E is equal to 0, we have the Weierstrass Gap Theorem. So, and now I'm going to give a sketch of this theorem, of the proof of this theorem. So we were able to prove that when n belongs to the set of gaps of GEP, then we have that n is greater than 0 and is less or equal than 2g minus the degree of E minus 1. And then we consider the sequence of these spaces. So as you can see, we are just adding the point P every time. So here we have 0P, here we have 1P, and we continue like this until 2G minus the degree of E minus 1 times P. So now we compute the dimension of one of these spaces minus the dimension of the space before that one. So we compute the dimension of the space OX E plus IP minus the dimension of the space OX E plus IP minus P. So we are taking minus 1 point. And we see that this is less or equal than 1. So that means that either these spaces are equal or the dimension of this space is bigger in 1 than the dimension of this space. So since we want to compute the cardinality of this set, we are interested in seeing how many of these spaces or of these ones are equal. So now we have that the dimension of this space minus the dimension of this space will give us the number of proper inclusions. So now we have that 2g minus the degree of E minus 1 minus the number of proper inclusions, all of these, will give us the number of equalities that are in this sequence. So if we compute all of this number, we are going to find that this is equal to the dimension of OX of KX minus E. And yeah, so that this is the sketch of the proof of this theorem, that the cardinality of the set of gaps is equal to the dimension of this space. And okay, I think that's all. Thank you. So yeah, do we have any questions? I think I went very
Okay,
fast.
so let's thank Brady for this talk with
Thank
a lot
you.
of gaps.
Yeah.